So, we're going to continue on with section 5.4. At the end of 5.4, we get into gas stoichiometry, which is, we've just learned about the ideal gas laws, 1 and 2 state problems. And now we're going to use the gas law to do stoichiometry with gases, or better known as gas stoichiometry. So here's our problem. And with any problem, the first thing we want to do is just look at the different numbers we have and identify what do those numbers represent. This is how you do problem solving. So we're going to identify our variables. We have two chemicals, nitrogen and sodium azide. And one important thing to note, whenever you see any of the Hofbrinkel gases, you want to think of them in the diatomic form. So when you read nitrogen gas, you should be thinking N2, not just N. Okay, so back to the problem. What do we know about each of these chemicals? Well, we were given that we have 60 grams of sodium azide, so I'll put that on the sodium azide side. Now the nitrogen, we've got this number 80 degrees Celsius. You should recognize that's a temperature. By the way, if you want to try to solve this on your own, just go on ahead. I would advise you, if you're not too sure, just stick with it for the first one and then you'll pause the video to try to do the second one on your own. Okay, so we have our temperature. We have to always convert to Kelvin when we're dealing with gases. We were given a pressure. You should recognize millimeters of mercury as a pressure. And what do we always convert to? It's sitting right here. I've already shown you. That's right, atmospheres. So we've got a pressure right here, which we're converting to atmospheres. And what else do we have? Oh, looks like that's all we've gotten. What are we trying to find? What volume? We're asked for the volume. So you look at this and you say, I've got temperature, pressure, I'm asked for volume. If you see all of these and you're not seeing any variable twice, you should think, oh, PV equals nRT. And you look at this and you say, what am I missing from this left side? Well, I'm missing N. If I could find N for nitrogen, N meaning moles, if I could find N, then I could use PV equals nRT. And you ask yourself, well, what here could get me N? Nothing here will directly get me N. Oh, but look over here. I've got these grams, and I've got a reaction. If I've got grams of a chemical, I could find moles of nitrogen using my reaction. So just looking at this information, we can use stoichiometry to get moles, and then we could use PV equals nRT to solve for volume, not for moles. Okay. And you can do this yourself or you can follow along here, but here's the solution. So here's solving for our moles of nitrogen, and then we're going to just plug that into PV equals nRT to get our volume. Now you'll notice I do not write out PV equals nRT. I always isolate the unknown, which is volume, and then plug into the equation. And these moles go in right here. Okay. Now, if you want to try this one on your own, you are welcome to do so. Whenever you have a reaction, if you have information about different chemicals, or we're talking about two different chemicals, set up two sides of information. So you'll notice I've got a hydrogen side and an ammonia side. And whatever you know about each chemical, write it down. So you can pause this and try it on your own. It's a little different from the first question. So let's see, what do we have? Let's just look at the left side for now. So we've got this 2.5 liters of hydrogen. That's telling us it's on the hydrogen side. Liters is volume. We've also got 25 Celsius, and that's about the hydrogen, not the ammonia. And here's a pressure, hydrogen, not ammonia. This right here, find the mass of ammonia, well, I put that down because the question was what mass of ammonia gas can be made from. So we're going to continue on. We've got our temperature. We always have to convert to Kelvin. We've got our pressure right there. always convert to atmospheres because the value for R in the ideal gas law has atmospheres in it. So now I've got a volume, a temperature, a pressure. What could I find if I have volume, temperature, pressure? I can find moles of hydrogen. If I can find moles of hydrogen, can I get grams of ammonia? You betcha, stoichiometry. So this time we're going to go backwards. We're first going to use PV equals nRT to solve for N. So notice I've isolated N right here. N is PV over RT, and then I plug in all my numbers. Notice I'm writing down all the units. Students tend to leave off the units, and then your answers end up wrong because you made some mistake and you didn't notice with your units that you made a mistake. Okay, so we get our moles of hydrogen. Notice again, hydrogen is H2 because it's a Hofbrinkel gas. And we're trying to get ammonia, so we're just going to go from moles of H2 to grams of ammonia using stoichiometry. I know you could do that on your own, so don't be lazy. Do that on your own. Pause the thing before you look at the solutions if you haven't already paused. And here is your solution. Okay, so we have moles, moles to moles, moles to grams. And why did I keep only 2 digits? Let's look. Why did I keep only 2 digits? It's not because of this 25. It's because of this 2.5 here. 2.5 liters. Notice with temperatures, your sig figs often change because 25 Celsius, when we add our Kelvin, we get 3 sig figs out of there. Remember with addition subtraction, we look at the placeholder. We don't count sig figs. I would not round this to 2 sig figs. I keep 3 sig figs in here. Because of the placeholder, it's more about keeping the answer to the ones place than anything else. It's not more about, that is the only reason. Okay, moving on. Dalton, famous person. Okay, Dalton's law of partial pressure. By the way, when you see partial pressure, don't think actually that you're only getting part of a pressure of a chemical. You're getting the total pressure of a chemical. But when you have a mixture of gases, the different chemicals combine to make the total pressure. So it's a part of the total pressure, but it's the complete pressure of a single chemical. Okay, Dalton's law states, what does it state? We're missing part of this here. Dalton's law states that when volume and temperature are constant, the total pressure of gas is the sum of the partial pressures of the gases in the mixture. So it's the sum of the pressures of each of the gases that makes up the mixture. So if we have 2 gases, A and B, and we put these together, we mix them into a container. Now we've combined them. This is just where I got that picture from. I made everything else up. So whatever the pressure here plus the pressure here will equal the total pressure over here, and that's what this says right here. It says PA plus PB is equal to P total, and if you look at the actual pressures that were given, 200 torr plus 300 torr gives 530 torr right there, and it worked. So PA would be called the partial pressure of A. Now again, it's actually all of A. It's the complete pressure that A is causing, but it's only a part of the total pressure, so we call it a partial pressure. This confuses many students every year, so if it's confusing you, it's very normal. I'll repeat this in class over and over. When I say partial pressure of a gas, I'm talking about all of that gas's pressure, but it's only a part of the total pressure, hence the word partial pressure. All right, so mathematically, Dalton's law says P total is PA plus PB plus PC plus ... if you have more than 3 gases, where PA, PB, and PC are the partial pressures of A, B, and C in the mixture of gases. Now, why do we really care? Honestly, this comes in when we're collecting gases over water. That's about the only time when we really care about this particular gas law. Okay, and what does this mean, collecting gases over water? All right, had to zoom out a little bit so you could see the whole picture here. Okay, here are 2 pictures of a gas being collected over water. In this picture, the solid is being heated, and then a gas is being formed, and the gas is going through the tubing, up through the water, filling this beaker. Now, originally, this is an upside down beaker. It was filled with water, and the water is being displaced by the gas that is bubbling up into this beaker. So let's see what we have here. So the water leaves the beaker as the gas enters the beaker. So there's this gas going up into here. You can take whatever notes you wanted to in this box of anything that I'm saying. So you had some space to fill in this information. So we have a gas being produced over here, and it is entering the beaker. Now, that gas is bubbled through the water right here. This is water. This is gas up here. Water molecules, gaseous water molecules, are also entering this beaker right here. So in this beaker, we have the gas that was being produced from a reaction and water molecules, because they were carried with the gas as the gas bubbled through the water and displaced. The liquid water gets displaced downward, but some gas water molecules enter the gas phase. So the total pressure in this gas area is the gas plus the water pressure. So the partial pressure of the gas plus the partial pressure of the water, which we look these up. The P water, vapor pressure of water depends on temperature, and you're always given that number, or you're told where to look it up. Now, the total pressure in here is equal to the outside pressure, the air pressure, because you should notice the water level in the beaker and in this container are the same. Do you see how it's leveled out here? So when you level out the waters between the beaker, the upside down beaker, and this big container of water, then that you know that the pressure inside this container, the air pressure outside, is equal to the gas pressure, the total gas pressure inside. All right. Here's another example. Now, you don't have to write exactly what I have in here. I'm going to talk about this. We have a reaction over here. The zinc and hydrochloric acid, they're reacting, and they're producing hydrogen gas, H2, because of Hofbrinkel. The hydrogen gas molecules are denoted by these double white balls, and the gas is coming through, and it's bubbling up through the water. And notice the water is the red for oxygen and 2 whites for hydrogen. So these are our H2O molecules all over here and here. And up here is our gas phase. So you'll notice little bubbles of gas are getting up into the gas phase, and the liquid water is being pushed down. So in the container, the water level is right here. In the beaker, the water level is right here. These two levels are not the same, so P total of the gas this time does not equal the air pressure, because the level here and here is different. So this level in the container is different from the level in the beaker. So the inside pressure here does not equal air pressure. We would have to get the water to come to the same level here, and then we would know that the air pressure was the same as the pressure inside the container. Okay, in any event, the total the total gas pressure in here is caused by your H2 molecules, your hydrogen molecules that were produced by this reaction, bubbled through the water, displacing the liquid water, and being collected in this bottle in the gas up here. And notice there's some water molecules in here too. See, you got a couple water molecules in here, because some of the liquid water will go into the gas phase. So inside, whenever you collect a gas over water, key words, you see collecting a gas over water, and you're trying to find the pressure of just the gas, you have to take the total pressure and subtract off the water pressure to get the gas by itself. Okay, that's just telling you where those pictures are from. There's another term you need to know, and then we'll do some problems. There's something called mole fraction, XA. Mole fraction is just like you think. Fraction is part of a whole, So a mole fraction would be the part of the moles that are A over all the moles. The fraction of all the moles that are only substance A. So there's our equation for mole fraction. XA is the symbol that we use for mole fraction. X is mole fraction. and the subscript is whatever substance. And mole fraction is just moles of the substance over total moles. You can do that with moles. You can also do that with pressure. So if you're trying to find mole fraction, you can actually do that just knowing the pressures. You don't even have to know the moles of a substance. If you know total pressure and pressure of a substance, you can get mole fraction. This equation can also be used to find the pressure of a substance if you're given the mole fraction and the total pressure. That should say total right there. There we go, that's fixed. If you're given mole fraction and total pressure, you can find the pressure of a substance. Okay, so let's do a problem. By the way, you know you're doing collecting a gas over water when it says something like in number 2, the gas is collected over water. This first problem, there's nothing about water in here, so we're not using the collecting a gas over water information. Okay, here's our problem. We're going to write down what we know. So what do we know? These are our given quantities, 0.5 atmospheres. That's our pressure of what? Of nitrogen gas. And 2 Hofbrinkel, don't forget the 2. Now, PT, the total pressure was given to us, whoops, as 1.30 atmospheres. That's our total pressure. And we are asked to find oxygen, mole fraction of nitrogen, mole fraction of oxygen. And you should be able to do that just using these equations, but oh, that equation and Dalton's Law, that the total pressure is the pressure of the nitrogen and the oxygen. You can pause this, do it on your own. I'm about to lead you through the solution. So first, we know Dalton's Law, total is the nitrogen and the oxygen. We plug in our numbers. This time I didn't isolate the unknown because it's just addition, subtraction. So we got the pressure of the oxygen. That was one of the things that we were asked for right there. Next, we're going to find the mole fraction. Easy! Pressure over total pressure. We had that equation right here. Mole fraction is pressure over total pressure. We didn't need to find moles. We could just use the pressure. So mole fraction of oxygen, pressure of oxygen over the total. Nitrogen, pressure of the nitrogen over the total. We get our mole fractions. Okay, another problem. Oops. Now, we've got a reaction and Dalton's Law all together and stoichiometry. So we're going to do stoichiometry with Dalton's Law. So we're combining what we learned 15 minutes ago with what we just learned about Dalton's Law. We're collecting a gas over water, so that's important information. We're going to have to do something special with what we have. First, identify your variables. So we had 24 degrees Celsius. That's a temperature. Convert to Kelvin. What else did we have? We had a volume. And if you want to solve this on your own, go ahead and do it. You can pause. All right, so we have a volume. We're going to convert that to liters because the universal gas constant has liters in it. We also have a pressure. Let's look at that for a minute. We have this outside pressure, which will equal the total pressure. And we're also given the vapor pressure of water. And we can use that to find the pressure of gas that's produced. And oxygen is the only gas that's produced. So the outside pressure is going to equal the water plus the oxygen. So let's see what we can do with that. So there's our total, which is the oxygen and the water, which is unknown. The oxygen plus the 22.4 millimeters mercury. We were given that this is the pressure of water. So I know 762 millimeters mercury is the oxygen plus 22.4. We can solve for the oxygen. And we need to convert this to atmospheres. I didn't show you that conversion step, but you should be able to do that. You just divide by 760 and multiply by 1 to go from millimeters mercury to atmospheres. And we still need to find grams of KClO, 3, potassium chlorate. We got a reaction. If I can get, let's see, I got temperature, volume, pressure. I can get moles. Use PV equals nRT to get moles. And then, you don't have to write down exactly what we're going to do, but we're going to get the moles. And then we're going to use stoichiometry to go from moles of oxygen to grams of potassium chlorate. Do that on your own. I'm going to show you the answers, but pause this, do it on your own, and did you get the right answer? Hopefully you did. All right, last thing for the day, kinetic molecular theory, also known as, when you hear me say KMT, I'm talking about the kinetic molecular theory of gases. Kinetic energy is the energy of motion, and kinetic, when you hear kinetic, you should think movement. Kinetic molecular theory has 4 postulates. They're all listed for you here. And we have an equation for kinetic energy. And I've told you right here what all these things mean. So the average kinetic energy is a constant times temperature, and it's equal to 1/2 times the mass of a substance times, this has a special name, it's the mean square speed. Okay, we're going to use this equation to do some things with diffusion and effusion. So first, what in the world is diffusion? Diffusion is you have a gas stuck in space, so you have a partition, you lift the partition, and now the gas molecules will diffuse over to the other side. Effusion is different. It is where particles, they escape through a hole like balloons. Why do balloons get small? Because they have lots of little tiny holes, and over time the gas molecules in the balloon escape out. So this is showing you how the molecules are escaping out to the other side. Okay, so our equation for diffusion and effusion is right here. And we're going to do a problem. We'll use this equation and that alone. A gas at a certain temperature effuses at a rate 0.25 times as fast as oxygen at the same temperature. What's the molar mass of the gas? Now, this is actually really, really easy. We're just plugging into this equation, but the key to this is setting up your initial equation. We're given that the rate at which the gas effuses is 0.25 times the rate of oxygen. You have to convert this sentence into an equation. So the gas effuses, our gas, at a rate 0.25 times as fast as oxygen. So our gas is 0.25 times our O2. And we're going to plug that in to this equation right there. You can try this on your own. So we have our equation. We know the molar mass of oxygen is 32. And our gas, we're just substituting this right here. Our gas, we're substituting in 0.25 times RO2. You should notice that the RO2 is going to cancel. We'll have 1 over 0.25 is the square root of the molar mass of the gas times the square root of over the square root of 32, which is the molar mass of O2. To solve this, and again, pause this, do it on your own. To solve this, we need to square both sides. So I've gotten rid of my r's on the left side. The right side I left alone, but I have to square both sides. So now I've squared both sides. And I want to isolate molar mass of the gas. And there we go. Molar mass of the gas, it turns out to be 512 grams per mole. All right.